Okay, so we've got one last video to do. This is the last 2 pages of section 3.4. And so this is pages 47 and 48 in the notes. So we left off having just discovered that any one of those complex eigenvalue derived straight line solutions produces a when you kind of expand it out and turn it into, in terms of real and imaginary, it produces 2 parts. And so we can state the general solution just using the parts from one particular solution. And this is the big reveal of this section. It turns out that we only need one of our straight line solutions. And from that, we get a part of it that's a real part, and part of it that's the imaginary part. And so notice all I did was I factored out the constant of I. And as we've said in the past in class, I is a constant. It's not a real number, but it is a constant. And our superposition principle was pretty clear. If you know one solution and you multiply it by a constant, it's also a solution. So I times one of these solutions is also going to be a solution. And so this must have a general solution that looks like, and so we're going to kind of put things together. This particular system that we started off with has a single particular solution, y1, that looks like this. And so from this one, we can kind of steal and drop the I here and treat each one of these as if they're their own straight line solutions and wind up with a general solution, y of t, that looks like this. We're going to stick a constant, k1, in front of this part. So negative e to the negative 2t sine 3t up top, and e to the minus 2t cosine 3t plus k2, another constant. These are constants for our parts. And then over here, it's just everything that's inside this matrix, e to the negative 2t cosine 3t. And in the bottom, e to the negative 2t times sine of 3t. And so what we're really saying here is this thing, if you imagine, really has kind of 2 parts. Just like we did before, we said that this is the matrix form, right, of the solution. Or the vector form, if you want to think of it that way. But you can just as easily rewrite this as a parametric systems. And again, we didn't start off knowing that this is dx dt and dy dt, but we're going to presume that's the case. So we have a dx dt equation in the top and a dy dt equation in the bottom. And all we do to get our dx dt equation is we kind of follow along, multiply k1 times the top plus k2 times the top, and that'll give me my dx dt equation. And so k1 with a negative in front of it, e to the minus 2t sine 3t plus k2 e to the minus 2t cosine 3t. And for my dy dt equation, all we need to do here is follow the bottom part. And that'll give us our dy dt. And so in this case, it's just going to be k1 times e to the minus 2t cosine 3t plus k2 e to the minus 2t sine 3t. And so again, we can write it in matrix or vector form, or we can write it in scalar, also known as parametric form. And so our solution can be written either way. And this is a general solution because we've got our constants. And so what's fascinating about this is you take a look at it and you think, okay, we've got e to the power, just like we're used to seeing in a solution, a straight line solution, but instead of having an eigenvector that we're multiplying by, instead of having a number like we'd multiply by for an eigenvector, we're multiplying it by another function, a trig function. And so if we want, we can manipulate this general solution a little bit further, and we can write our big Y of t. I'm just going to kind of say, you could also kind of, with a little bit of factoring, you can write it as e to the minus 2t. And then I'm just going to combine, factor out e to the minus 2t from each one of these, and then combine those two matrices. And so up top it'd be minus sine 3t plus cosine 3t. And in the bottom, it's cosine 3t plus sine 3t. And so look at what we have by manipulating our general solution. Oh, sorry, I forgot my K1s and my K2s in there as well. Darn it. I'm going to have to go through and insert those. So apologies, it'll just take me a second. So I'm going to hit pause while I do this. You guys don't need to watch me do it. Sorry about that. With a little bit of modification, we can turn that into a single matrix, right? So e to the negative 2t, that's a multiple that the whole thing has in common. And take a look at what this gives us. This gives us kind of two chunks to take a look at. The first chunk, let me see if I can find a color that I haven't written in here. The first chunk is really exponential. But what's it doing? It's exponential decay, right? So this is exponential decay over time. So as t gets bigger and bigger and bigger, this term says it's going to get smaller and smaller and smaller and smaller. So we're basically multiplying all of this by a smaller and smaller and smaller amount. So what does that mean for the second part? What does that mean for all this stuff over here? Well, all this stuff over here, notice it's just constants times sines and cosines. And no matter what you do, as t gets bigger, sines and cosines just kind of oscillate. They go back and forth and back and forth. They up and down and up and down. So sine and cosine don't approach any particular value as t approaches infinity. So really, this is just a wobbly part, if you want to think of it that way. This is wobbly in a periodic fashion. And so over time, you have exponential decay multiplied by a periodic wobbliness. So what would you get if you wanted to imagine exponential decay and periodic wobbliness? Well, if you look at your dx dt, this is exponential decay times periodic wobbliness. And what you're going to get as a result of that is our x versus t curve is going to go, and it's going to slowly kind of wobble down to close to the origin, right? And our y is going to do exactly the same thing, exponential decay times periodic wobbliness. And so the y versus t graph, you would expect to go and slowly decay away. Both of them are decaying away. And so what does that leave us with on the phase plane? That leaves us with exactly what we expect from the second page of the notes. I'm just kind of quick throw that up there, which is the x-coordinate gets smaller and smaller and smaller, while the y-coordinate's getting smaller and smaller and smaller. Both of them are decaying away towards the origin. And so no big surprise, you wind up with exactly what we see on the phase plane. We see not straight line solutions, but spiraling solutions. But here's the good news. After all is said and done, we were able to write our general solution just by looking at one complex eigenvalue and eigenvector. We never actually need to bother with the other complex eigenvalue. We only need lambda 1 and the associated eigenvector v1 to find the general solution. And so that's really good news because it cuts down the amount of work that we have to do. That's always a nice thing. So on the next page, and this is the last page for the section, we're going to kind of bring it all together and talk about that spiraling. What's up with the spiraling nature of these? It turns out that the spiral is actually coded into the eigenvalues themselves. So early on when we looked at it and we said, so what about this? Lambda 1, if you remember, was equal to -2 plus 3i, right? And we looked at it and we're like, how do we see that on the phase plane? Well, it turns out that both of these numbers tell us something really important. The -2 appears in the general solution. That's the -2 right there. And, go figure, the 3 from right there appears right here. So you can tell just by looking at the eigenvalue that this thing is going to spiral in towards the center because it's negative, it's decay. And this thing right here tells me how quickly it's wobbling, how quickly it's spiraling. And so inside this little table, it lays out kind of all the information that you need. So if you have a complex eigenvalue of this form, alpha plus I times beta, and we're just going to say beta is greater than 0 because if it was less than 0, then it would be still plus or minus. It's not going to change anything. It turns out that the solution is going to spiral about the origin of the phase plane with a period of 2 pi over beta. And so that means for our example, at the very bottom of the page, you'll see, for our example, the period was 2 pi over the beta. And the beta from our eigenvalue up here was the 3. And so all we'd have to do is write 2 pi over 3. That is the period of the frequency. The period of the frequency, the period of the solution curves as they spiral around the center. The other piece of information that's super useful is what about that alpha? And so the alpha becomes useful because it's able to tell us if alpha is greater than 0, we have a sink. If alpha is, did I say greater than? I'm looking at it, it says less than. If alpha is less than 0, we have a sink. If alpha is greater than 0, we have what's called a source. And there is a special case where alpha is exactly equal to 0. And what would that mean for our complex eigenvalue? That would mean that it doesn't have a real part. It's only imaginary. And at that point, instead of having a spiral in or a spiral out, you would have a center. It's basically a bunch of circles or a bunch of circular-like figures. It's possible they could be ellipses, right? So A equals 0 or alpha equals 0, that implies the eigenvalue is all imaginary. So while the period of the spiral refers to the amount of time that's required for one full cycle to go around, remember, it's not going around in a full circle. It's going around, if it's spiraling in, it might go and then get really, really close to the origin. It might be hard to see that period. But you can play with Maple and actually adjust the settings for t goes from 0 to 2 pi over 3. And you can actually see a solution curve will go one rotation around and stop. And of course, frequency is just the reciprocal. So if you know the period, then you also know the frequency. Frequency in this case would be 3 over 2 pi. And period and frequency have reciprocal values, but they also have reciprocal units. So period would have units of time, frequency would have units of inverse time, right? So I strongly encourage you to check out the Maple Notes page for this section and see the stuff that I did for this section. I try to explain some things in more detail using Maple so you can kind of visualize what's going on. But that's it for 3.4. We learned how to find the general solution for situations where we have complex eigenvalues and their corresponding eigenvectors.